Good afternoon. We want to welcome everybody to the GTI Project Spotlight event webinar. We're going to be highlighting 3 projects today. Our host is Dr. Randall Gensler from Georgia Tech. Dr. Gensler.
Thank you. Welcome everybody to the Spotlight, the Project Highlights speaker series. I'd like to welcome today Dr. Jay Kwan from Kennesaw State, Dr. Steve Durham from UGA, and Dr. James Tsai from Georgia Tech. They're going to be talking to us today about their research projects, going through the highlights, and we should have some time for questions at the end. In order to save video bandwidth, if you could go ahead and turn off your video, unless you're asking a question at the end, and go ahead and turn off your microphones. And with that, I'm going to be short in my introductions because I'd like to make sure that all of the speakers have time to get through their materials. So Dr. Jay Kwan is from Kennesaw State. He's a Department of Civil and Environmental Engineering, specializes in geotechnical engineering with research interests in characterization of and sustainable use of geomaterials, structural pavement performance monitoring, and non-destructive testing. His talk today is going to be looking at the performance of full depth reclamation pavement analysis. And with that, I'll go ahead and turn it over to Jay. Thank you.
Hey, thank you very much for the nice introduction. This project was started in 2018 and ended last year. I'd like to share some of our findings. The full depth reclamation is the process to pulverize old and damaged pavement section and reclaim, and then mix with the stabilizing agents such as like a dry cement or the foamed asphalt to creating a stiff base course. And this base course will be served as a new base course for new pavement sections. And this process became very popular in the recent years because the process is quite simple, and then it offers a lot of economical benefits. You don't have to export the old pavement materials, and you don't have to import the new paving materials. The entire process can be done within 2 weeks, so there is another savings in terms of in terms of the safety and then the cost as well. The DOT introduced a supplemental specification in 2018. This section 315 is included in our standard specification, and this specification addressed the mixed design and the construction requirement and the quality acceptance criteria. As for the FDR mixed design, the contractor required to obtain the samples in every 1,000 feet and to determine the required cement content to meet the strength values. In the state of Georgia, we require unconfined compressive strength, a 7-day unconfined compressive strength of greater than 300 psi. But when you look at those existing pavement sections, in general, most of the pavement sections are not uniform, means that the thickness will be varied by locations. Subgrade strengths generally vary significantly, and therefore the base course, the thickness, density, is going to be very significantly. So therefore, even though the contractor was precisely processed the existing pavement sections to the target depth, and then also apply the target cement content, but because of the inherent variability of the parent material, there will be some variability in the finished FDR base course. So the motivation of this research is to assess the variability in the properties of the FDR layer and investigate its impact on the pavement performance. So the research team at the KSU assisted quality control activities for a new FDR pavement section, and then we obtained field samples and bring it to our laboratory to measure those unconfined compressive strength values of the FDR base. And then also we utilized those deflection tests, such as lightweight deflectometer and the falling weight deflectometer, to monitor the stiffness gain over the time. Based on this field observability, we conduct the mechanistic sensitivity analysis, again, to investigate the effect of the variability in the FDR properties on the pavement performance. So as for our field study, we select the State Law 70, located in the Fairburn, Georgia, which is southwest of the city of Atlanta. This about 4-mile road was processed in 3 days. And each day, the research team go out and then select the first 500 feet as a test strip And then we obtain those field samples from the test strip, and then also monitoring the stiffness changes using the deflection testing. This is the photo before FDR process. And as you can see, the asphalt is highly oxidized by indicating by the light gray colors, and they have a lot of cracks on it. And this is the photo after the FDR project. Let's talk about this construction. The construction is begin with this milling of those existing asphalt sections. And the reason that we want to mill off those existing asphalt concrete is because when you pulverize all the pavement section at once, then asphalt will remain as a big chunk. And then when the asphalt and then the base course is just pulverized at the same time, it's very difficult to meet the target gradations, because the larger chunk of the asphalt will be just floating around the base course and then some mix of the fines. So therefore, in general, they just mill up those asphalt concrete and then start to pulverizing it. The contractor, even though it was not required, but the contractor generally performed the so-called premix. The purpose of this premix is basically to produce more uniform the gradations and to identify some soft spots, and then also some utility line that was not shown on the map, and then to address these issues before the actual FDR process. And the day of the FDR process, the dry cement is placed, and then the amount of the dry cement was validated using the square yard, the Croth method. So basically, you're placing the square yard of the fabric, and then collect the cement, place it on the square yard of the fabric, and then measure it to verify the target, the dry cement content was placed. This is not very scientific, but it seems like it works great. And after that, the entire pavement section was stabilized, and the reclaimer is pushing the water truck, and then behind the reclaimer, those series of rollers is follows: the ship's-full rollers and the smooth drums, and then the pneumatic tire rollers is follows. And after that, the primer is just placed sprayed on top of this to finish the FDR base. The purpose of this primer is to protect prevent those moisture loss during the curing of the FDR base. And before you're placing those asphalt concrete, in state of Georgia, we use the chip seal layers. The chip seal layers is to provide the temporary the driving surface, but also designed to serve as like a bond breaker, because the cement treated base will be prone to have like a shrinkage cracks, and then those shrinkage cracks without the bond breaker, we're gonna reflect it to these finished asphalt concrete sections. To avoid this reflective crack, we use the chip seal layer. This is common in the state of Georgia and then also the state of South Carolina. In the other state, like California, they use so-called micro cracking. The micro cracking is simply you utilize the vibratory rollers on top of the finished FDR base to create a lot of hairline cracks. And this process was evaluated by the Louisiana Center for Transportation Research Center, and they kind of like found out this mixed the result. Some cases the micro cracking works great, but in some cases the micro cracking is not works. So therefore, we stay with the chip seal layers. And after that, we're placing the asphalt. This is how the entire construction process ended. All right, let's talk about the field core and then uncombined compressive strength values of the field cores. Again, the entire pavement section was processed in 3 days. So there's 3 construction strips. And we took those cores in 1 day. So therefore, you're going to see the curing period is different from 7 days to 5 days. So the 7 days curing, let me just bring up my pointer. For this, from the first strip, and as you can see, the target UCS values was met or exceeding. And in the case with the test strip 2, the construction strip 2, the UCS values are generally lower than the target UCS values. And the test construction strip number 3, even though it has the only curing days of 5 days, but you're gonna see that most of the sections are met those the target UCS values or exceeding the UCS values. We also utilize the deflection data test, and then the deflection test we use the LWD lightweight deflectometer. In this case, the lightweight deflectometer, the weight of the plate is only 2,200 pounds, and the falling weight deflectometer is to use to kind of like simulate those the design axle load or the design wheel load of 9,000 pounds. And the GDOT recently obtained those the fast FWD, which can perform the falling weight deflectometer test more quickly compared to the traditional falling weight deflectometer. Let's take a look at the lightweight deflectometer test result. This slide shows the dynamic deflection modulus shown on the vertical axis, and then on the horizontal axis is the curing period. As you can see, as the FDR base is cured, and then the strength is gained. So test section 1, you're gonna see the strength gain over the curing period. Whereas in the test section 2, if you remember in the previous slide that has the lowest UCS values from the fielded cores, it does not gain the stiffness up to like about day 2. And then over the day 3 and day 4, it gains us the stiffness values. And the section 3, even from the day 1, the section already get a high modulus values. When you look at those the deflection measured from the lightweight deflectometer, and the deflection is going to be generally reduced as the base course is cured. And the test section 1, the error bar indicating high variability. The variability is also going to be reduced as the stiffness gain, and then the deflection is reduced. Test section 2, you gain the minimum deflection of 0.01 inch. And then the Indiana Department of Transportation, they utilize the lightweight deflectometer as for a compaction acceptance criteria. And for a cement-treated base on the soil, they recommend that the maximum deflection under the lightweight deflectometer should be less than 0.01 inch. So therefore, we can say all the sections, even though test section doesn't have the modulus values from or the UCS values from the cores, but we all meet those the deflection criteria according to this LWD. And let's take a look at the falling weight deflectometer. As for the falling weight deflectometer, we didn't back calculate the modulus of the base cores. Instead, we used those impulse stiffness modulus, which basically indicating of the stiffness of all the layers, FDR base and then the subgrade. And we performed those FWD in 1 day. So it is not a comparison between the same section over the times. It is basically the measure FWD, the data from different location of the construction sections. Now we can see those at the 0 day to the 7 day, overall ISM values has increased. And then at the same time, the coefficient of variation is decreased. So even though this is not measured at the same locations, it's prudent to assume that the variability will be reduced as time goes by, and then also the stiffness will be increased. Based on this, the observed variability, we performed the mechanistic analysis. In this case, we used the Julia, which is the structural engine, including the Ashtware, Pavement ME softwares. And as for the critical location, we look at the bottom of the asphalt concrete, and the bottom of the FDR base, and then top of the subgrade. The base modulus was varied from 400 KSI to 600 KSI, and then the base thickness varied from 8 inches to 12 inches. And as you can see it, this is the strains at the bottom of the AC. We look at the horizontal strain and then the vertical strain, and the strains are generally reduced as the thickness increases and then as the modulus of the base course increases. When you look at the horizontal strain at the bottom of the asphalt concrete, as the base modulus greater than like 600 KSI, we can say this pavement section will be considered as like a perpetual pavement section, meaning that there will be no chance the FDR base and the subgrade will be failed. We just need to mill and fill the wearing surface. The vertical strain is also going to be decreased as you increase the base modulus and the thickness. Similar trend was found on the FDR base layer as well. The strain at the bottom of the FDR base reduced as the base modulus increased, and then also the base course thickness increased. And then also the vertical strain at the top of the subgrade generally reduced with the increase in the modulus and then the thickness of the base. So everything was just kind of, reasonable, the trend. So here is my summary of the observation. The laboratory and the field test shows that the modulus of the FDR base increased with the times as the curing period increased. But after 5 to 7 days, the variability of the UCS and then the deflection the measurement becomes reduced. And the very little no tensile strain at the bottom of the asphalt, the concrete layer, indicating that asphalt will not gonna experience bottom-up types of cracking. In this case, we have a very stiff base course, so that the primary mode of the failures in this case will be the asphalt loading on this pavement sections. As the FDR base thickness and base subgrade modulus increase, the asphalt concrete will absorb most of the vertical strain, and therefore you need to do some periodic maintenance of the asphalt concrete. Based on this observation, we made the following recommendations. The first one is going to be the premix definitely going to be required in FDR constructions. You see this, during the premix, we hit the water line. It was not shown on the utility maps. And this purpose of the premix, again, to identify some soft spot and then the utility lines that was not shown on the utility maps. So we were able to address these issues before the actual FDR process. And we think that more stricter restriction on the thickness should be implemented in this case, because in this table shows the UCS values was presented in the previous slide, along with the thickness. The target design thickness was 10 inches. And as you can see, in all the sections are generally greater than 10 inches. So therefore, increasing in the treatment depth without increasing the amount of the cement, therefore you can have the reduced percent cement on the mix, and as a result of that, you see thus the modulus, the UCS values, especially on the test strip number 2, was much less than compared to these other sections. We recommend using the phenolphthalein, the indicator solution, and actually the DOT already using it to verify the treatment depth. And section 315, the thickness tolerance already addressed the thickness requirement. And then LWD and FWD should be performed to monitor the stiffness characteristics. Even though the LWD has some limit because of the weight of the plate is very lower compared to the FWD, but I think it's a good tool to be utilized to identify some soft spot before it is 7 days of the curing period. And the final recommendation is we need to do the additional research to incorporate this FDR into the pavement design. And state of DOT, the Georgia, we use the Ashton pavement AME, but still we're using the layer coefficient and the structural number design process. According to this, the pavement design manual, the cement stabilized the grade aggregate has the layer coefficient of 0.22. The accuracy of this layer coefficient should be verified. And in the case with the ME design, it is kind of unclear how to model those FDR bays. FDR can be cement treated aggregate or can be considered as a solid cement. So therefore, it is kind of in somewhere in between though. But depends on how you characterize those materials. There is a recommended test protocol. It's going to be different. And then also for a solid cement, you have to get the modulus values from the correlation equations. So these are the correlation equations. So based on the UCS values, in the case with the solid cement, if we're using those targets, the UCS values of 300, then it's going to be 360,000 PSI values. But this is kind of like a gray area, so therefore we need to do some further investigation. And the DOT sponsored another research project to the KSU So I'm working on this new project to find out the method to incorporate the CSRB into the pavement design. And hopefully next year or on the following year, maybe I have something to share with you guys. So this is all I have. And I would like to take some questions.
Thank you, Dr. Kwan. I think we're going to go ahead and wait for questions until the end. Hopefully we'll have some time at the end. We can extend the session. I would be remiss if I didn't mention that this series is sponsored by the Georgia Department of Transportation and the Georgia Transportation Institute, which is the multi-university consortium that works on research with a variety of the state agencies. So having Kennesaw State as well as UGA and Georgia Tech here today is great. I'd like to introduce Dr. Steven Durham. Dr. Durham is from UGA. He actually led the development of the new civil engineering degree program there through its first accreditation in 2015. He's currently the Associate Dean for Student Success and Outreach in the College of Engineering, and also a professor in civil engineering focused on structural engineering, concrete materials, sustainability, and construction management. His project today he's going to be talking about is the use of fiber-reinforced rubberized concrete medium barriers in dissipating the impact energy to improve driver safety that are involved in crashed vehicles. So with that, Steven, go ahead and take it away.
All right, excellent. Well, thank you guys for being here this evening or this afternoon. And just want to share a bit of our research where we're investigating use of recycled tire chip and fiber reinforcement for concrete barrier walls. I want to acknowledge some of our collaborators. Dr. McGim Trezeppa served as the co-principal investigator on this project. We also had graduate students Alex Blankenship, Grace Darling, Victor Lopez, and Tofel Ahmed. And I also wanted to acknowledge our partners at GDOT, which include the Office of Research, the Office of Transportation Operations, as well as the Office of Materials and Testing. In 2016, there was an update to the AASHTO MASH manual, which saw a 58% increase in the impact severity for test level 4 compared to the NCHRP 350. And so our research really was to investigate the utilization of tire chips and fiber reinforcement to dissipate that impact energy and improve driver safety. There. I guess. Go to the next slide here. And so this study here set out to build upon our phase 1 study, which really looked at only utilizing recycled tire chips in concrete mixtures. It also only looked at it from a materialistic standpoint, where we only performed tests on fresh and hardened concrete properties tests on the mixtures themselves. So this is to really kind of scale things up a bit from that phase 1 study. In this phase 2 study, as I mentioned, we also brought in or included fiber reinforcement in combination with a recycled tire chip. We also developed a nonlinear finite element analysis model for crash simulation for vehicle impacts, where we looked at impacts with pickup trucks as well as single unit trucks. And we want to use that to simulate that impact to determine the impact performance of this rubberized fiber reinforced concrete for barrier walls. We were able to validate the analytical model that we developed through the construction of both scaled laboratory beams and barrier walls that utilize that rubberized fiber reinforced concrete. We also, at the end of the study, investigated the influence of steel fibers by themselves on the fresh and hardened concrete properties. And we also looked at its influence on load deflection behavior, as well as enhancements to flexural and shear capacity. And then lastly, we deployed a machine learning methods process to develop an accurate prediction model for compressive strength and modulus of rupture for steel fiber reinforced concrete, ultimately developing a web application tool that can be used by materials to estimate what those properties are, and again, kind of weigh the benefits of the performance to that of the cost by including the steel fibers. Ultimately, in this research here, we developed or batched over 30 different concrete mixtures, 25 different concrete beams for static and impact testing, 2 concrete barrier walls, a series of finite element models, as well as a machine learning application tool. So in our early part of this research phase, we investigated, as I mentioned, the rubberized fiber reinforced concrete material. As you can see on the left-hand side, the compressive strengths all exceeded the GDOT Class A minimum threshold of 3,000 psi, and the majority of the mixtures did surpass the Class AA 3,500 psi threshold. We did see some decrease in strength with the polypropylene fibers, which was a little bit lower strength compared to the steel fiber that we did use. So steel fibers seemed to be a bit more superior. I think the polypropylene fibers generated a bit more harsh of a mix, more difficult to work with and consolidate. So there could have been some issues associated with that. We did see in the middle here, you see the modulus of rupture values. We saw an improvement in the modulus of rupture or flexural capacity of our concrete by incorporating the fibers, specifically that of the steel fiber. We saw great benefit in and around the 1% or 0.75% of steel fiber with the inclusion of about 20% tire chip. And then on the right-hand side, we saw a significant improvement when we utilized both steel fiber and recycled tire chip in terms of impact resilience. This impact resilience was measured by a drop hammer test where we would basically count the number of drops on a small concrete puck that was 6 inches in diameter, and we would measure the time to initial crack, separation, and complete failure. From the material testing that we had, we scaled up to doing 8 static beam testing on our rubberized fiber reinforced concrete. You can see images of these beams on the left-hand side. We subjected them to a 3-point bending. We used the load cell. We used motion capture to be able to capture kind of the deflection and other things there. What we found from this static testing was that the control beam without any rubber or without any fiber had the lowest toughness of all specimens tested, whereas the specimen with 0.75% steel fiber and the 20% tire chip saw the greatest static energy dissipation of all beams there. All beams ultimately did fail in flexure, and so we did get the type of failure that we wanted from that, but we did see an improvement in load capacity, a slight improvement in load capacity, as well as a decrease in deflection when the fiber was utilized. Beyond the static testing, we fabricated 6 beams for dynamic impact testing here. Impact testing was tested through the use of a 400-pound weight that was dropped at a height of 20 feet. The test setup was instrumented with a load cell, accelerometer, and motion capture. You can see some of the points here for our motion capture here right along the center. We're able to capture deflection. In this test here, we're able to basically examine the performance of the concrete when subjected to that impact. The type of impact failure that we wanted to see was shown near the bottom of the screen with the steel fiber 1%, tire chip 20%, where there was only minimal flexure cracks. We didn't really have any concrete chunks fly off or anything of that nature, so it really performed the way that we wanted. So we saw a great benefit by incorporating both the steel fiber and the tire chip. We also measured the mid-span deflection. So with the mixture that did not have, for the beam that did not have any steel fiber in it, only 20% tire chip, we did see a slight increase in the displacement, about a 5% increase. However, when we incorporated both the fiber and the 20% tire chip, we saw a 56% decrease in mid-span deflection. So we saw the benefit there. So some conclusions from this early phase of our work was that the steel fibers were most effective in improving flexural strength with moderate or very mild improvements in compressive strength, but we did see some improvements in impact resilience when in combination with that of the tire chip. We did see some increase in ductility for the static beams when incorporating the steel fiber and the tire chip. We were able to, through the inclusion of the steel fiber, increase the flexural capacity and reduce deflection for the beams. And when we did include the fiber, we were able to increase the reinforcement ratio, which ultimately resulted in a doubling of the static energy dissipation for those beams. And then with the impact beam testing, our conclusion was that when used with steel fiber and tire chip, that we were able to significantly reduce the impact forces, increase ductility, and more effectively decrease energy or distribute the energy across a larger area of the concrete beam. Once we finished that earlier phase, we actually ran the next 2 things I'm going to talk to you all about in parallel. So one of the things that we did was developing a finite element model. That phase of the study really developed, or initially developed, with evaluating a material model that was most appropriate for our fiber reinforced rubberized concrete material. So we did play around with some different material models that were out there. Once we took those models, we compared those models against some of the experimental data that we had and found one that we feel very confident with. Once we found that model, then we built a model, a barrier wall finite element model that you see here on the left-hand side, subjecting it to an impact. We really tried to model what we were doing in our laboratory, so we were subjecting it to really a kind of a plate load across at the height of the barrier wall there. We ran several simulations until we found a velocity that would produce the type of impact load 150 kips, which is similar to what we found in other literature. Under the similar parameters, we found that same velocity and same impact produced a force of 136 kips when we looked at the rubberized fiber reinforced concrete compared to the control that had no tire chip and no fiber there. The peak stresses, you saw a reduction in the peak stress after impact with the rubberized fiber reinforced compared to the control that didn't have that. So we did see, again, benefit when incorporating the tire chip and fiber in the mixtures there. Once we, again, kind of built off of the laboratory modeling of the barrier wall, then we scaled up to looking at running crash simulations using pickup trucks and single unit trucks. In this part of the phase here, we subjected the barrier wall to an impact force from a pickup truck. We found that the impact force from that pickup truck generated for the control about 168 kips, whereas we saw a significant reduction in the rubberized fiber mix of about 41 kips. The modified barriers with the steel fibers and tire chips experienced a less deformation after post-impact. And then for the single unit truck, we found that the model the barrier wall would, my lights went off in my room. Hold on just one second. And so my apologies for that. And so the barrier wall, when subjected to the single unit truck, was damaged, but did not allow the single unit truck to penetrate the wall. So some conclusions from this part of the phase was that the steel fiber reinforced concrete did reduce the impact force. In combination, fiber and tire chip saw a reduction in post-impact peak stresses. And the analysis results indicate that the rubberized fiber reinforced concrete median barriers that have undergone pickup truck collision are able to successfully resist those impact forces, as well as to be able to prevent a penetration of a single unit truck. However, you did see some significant structural damage to the wall with that unit truck. As I mentioned, we did perform some experimental testing. And again, we were looking at this in combination with the finite element model here. So we constructed our own full-scale barrier walls in our lab, tested them. We instrumented the barrier wall with embedded strain gauges, as well as motion capture system, and then subjected it to, by putting an impact force, by putting a steel plate on the end of our actuator and subjecting it to that dynamic impact. The results from this was that we found that the majority of the impact load was carried by the vertical reinforcement across the shear key of the barrier wall. We saw a 56% increase in the tensile strain on that vertical reinforcement, where we saw negligible strain on the horizontal rebar. The most significant part of this was that we saw that the inclusion of those steel fibers distributed that load across a greater area than with the control beam or control barrier. And that type of findings was very substantiated from some of the earlier work that we had done, where we looked at simply the beam testing in our lab. We did measure displacement, and so while the rubberized fiber reinforced concrete barrier saw a higher initial midpoint displacement, it did see an overall decrease in displacement compared to the control wall. So we did see a decrease in the overall displacement by about 38% when compared to that of the control barrier. So some of the conclusions from our experimental testing was that both control and the rubberized fiber reinforced barriers produced no visible damage on the surface there as a result of the impact and the dissipation of energy from that impact. The presence of steel fibers did increase the area under compression along the backside of the barrier, where we saw about a 20% reduction in the maximum strain. Maximum tensile stresses, compressive strains along the backside, and the reinforcement were experienced under similar loading conditions for both the experimental and what we saw in our finite element model testing. And the barrier saw a 53% increase in the initial displacement, while we saw an overall decrease in the total displacement when used the rubberized fiber reinforced barrier. Overall, we saw that the rubberized fiber reinforced experimentally performed just as well as the control barrier, despite having 100% lower compressive strength. So we did have concrete that was substantially lower strength than that of the control, but they performed equally the same. And our last part of our research study here, and we kind of divided this last phase here into 3 subsequent phases. In the initial part, in this part here, we only looked at steel fiber reinforced concrete in the absence of any tire chips. So we took kind of the rubber out of the fold here, looked at it only with steel fibers. So the initial part of this was we investigated 12 different concrete mixtures incorporating steel fibers. What we looked at in terms of variables were end anchorages, aspect ratios, and fiber volume fractions. And we measured the fresh concrete properties, the compressive strength, modulus of rupture of those concrete mixtures there. Once we gained enough knowledge from that, then we moved on to phase 2, where we developed a series of large-scale steel fiber reinforced concrete beams and subjected it to a third-point loading, static loading. And then we wanted to understand that steel fiber's influence on load deflection behavior, as well as the enhancements to the flexural and shear capacity of the beams. And then lastly, what we did was we took a lot of published data that's out there, some of our own data, and developed a database, and then employed a machine learning method to develop a prediction model for estimating what the compressive strength and modulus of rupture is for steel fiber concrete. And from that, we were able to take a database, apply 80% of that data to training the machine learning, and then using 20% to test that to develop a pretty accurate prediction model there. So from our results here, you'll see that on the left-hand side, the compressive strength and modulus of rupture values for steel fiber increased substantially over the control without fiber. So we saw a great increase when incorporating the fiber. We saw our greatest benefits when using 4D and 5D fibers. What that means is that just adds extra end anchorage to the fibers there. And so we saw some better benefits there. In the middle part of your screen here, you'll see some of the load deflection figures from our static beam testing. And what we found here was that we were able to adequately increase the shear spacing of our shear stirrups when including the fibers and getting the same level of load capacity and same type of failure. So by incorporating the fibers at 0.75% minimum up to 1%, we saw just a similar type of performance as if we had shear stirrup spaced as they had previously been designed there. And you can see some of the testing on the right-hand side. So we were able to manipulate the failure mechanism or behavior by incorporating the steel fibers in there. As I mentioned as well, again, we took data from over 100 published studies, gathered that data, analyzed it, and used machine learning to really develop a prediction model for estimating what the compressive strength and modulus of rupture is. From that prediction model, you'll see up here on the top right some of the compressive strength predictions. We compared our prediction values against values generated from some pretty well-published prediction equations that are out there. And we found that our prediction values were very close. In fact, our predictions came within about 10% of actual experimental test results, whereas those other prediction equations were somewhere between 15 as high as 30% variable. On the bottom right, you'll see a web application tool that we generated. We felt that it was productive to generate this web application tool to estimate the modulus of rupture and compressive strength by changing different variables. So this tool allows you to change the material properties like cement proportion, the coarse aggregate, fine aggregate, water cement ratio, as well as the fiber. So this is only good for steel fiber, but you can change the fiber length, fiber aspect ratio, as well as the volume fraction within your concrete. You also have the option to add in material costs. So if you know the cost of your cement, rock, sand, you can add those costs in there. And what it'll do is it'll give you the ability to be able to estimate what your performance is while also weighing the added cost of adding those fibers in there. So it gives you kind of a leg up in some preliminary investigation before you actually start doing some laboratory type work. So the outcomes from this work here was that our compressive strength increased the fiber volume. As the fiber volume increased, we saw fiber volume in and around about 0.75%. When it was only steel fiber, finding the compressive strength very well. Shorter fibers were better for compressive strength, whereas the longer fibers were better for flexural strength. Flexural strength did increase with the increase in fiber volume. We did see that the still fibers could be used as a partial replacement for shear stirrups. In essence, we're able to, with a 0.75% volume of still fibers, increase the spacing of shear stirrups and still have the same type of load capacity and failure. Of the prediction methods that we had, we used a gradient boosting method model, and that we found that was the most accurate in predicting our compressive strength using our machine learning process. And that prediction application was created to allow for a more efficient method for developing still fiber reinforced concrete. So I know that was a lot of information to digest there, but if you have any questions, we can take that maybe at the end of today's session. I appreciate your time.
That's great. Thank you, Steven. All right, our next speaker is Dr. James Tsai. James is a professor in the School of Civil and Environmental Engineering here at Georgia Tech, and is also an adjunct professor in the School of Electrical and Computer Engineering. He helps to coordinate the dual degree program between those two. His research focuses on remote sensing and computer applications for infrastructure assessment and management. He's going to talk to us today about two projects. One is assessing and analyzing the change in traffic sign retroreflectivity conditions over time, and analyzing the change of pavement surface distress using 3D sensing data collected on Georgia interstates. James, you all set?
Okay, Randy, thank you. Hello, everyone. Welcome to our presentation. And our research focuses on the transportation infrastructure health and safety condition assessment and asset management. Today, I think we focus on in the infrastructure health condition assessment. So I would like to present our GDOT Research Project 1732 regarding validating the change of sign and pavement condition and evaluating the sign retroreflectivity condition assessment on Georgia's interstate highway using 3D technology. So this project has been selected as 2020 AASHTO High Value Research Project, and because it's a significant impact on maintenance, management, and preservation. So specific focus on this project here is one is automation of the health condition assessment and using 3D sensing technology. I would like to acknowledge the sponsor of this research project from GDOT, especially the maintenance office and material testing and research office. And I would like to also acknowledge my research team and they working on this one here. Without their effort, this would not be able to achieve. So I'm going to presenting the following objective background and then two content there. One is focused on the traffic sign retroreflectivity condition, which is nighttime visibility. This is kind of related to safety condition too. The second one here is related to the pavement surface distress. At the end, I will talk about the impact and benefit of the research. So as the research objective here, it's kind of still focused on two. We want to see the change in the condition assessment about a traffic sign, the retroreflectivity condition, which is nighttime visibility condition assessment. The other one there is related to pavement distresses, and then we collect the data for the entire interstate highway in 2015 and 2018, respectively, to perform this analysis. So kind of give a little bit of background information. We are using this Georgia Tech sensing vehicle. This is the integrated through the research project sponsored by US DOT. So in this sensing vehicle there, we have the 2D imaging system for camera and 3D laser scanning for the pavement condition, as well as the 3 LiDAR technology, as well as IMU, GPS, and DMI. So I think the keynote I want to mention about is nowadays, I think there's different sensor data that the one I just mentioned about can be collected in one single run to optimize the data collection effort. So you can assess the sign condition assessment as well as the pavement condition. You just need to drive once. So this one here is specific for the payment, 3D payment service data. So this is a new, now it's become, through our 10-year study, now become a national standard and become in the US. So this one here, you can see the high resolution 3D data being collected using the laser technology. It can automatically extract the cracking and rotting, as well as IRI smoothness and faulting, raveling, etc. So the key thing here, the keynote there, I think the focus is not only the data collection, but processing and analysis. And the other keynote is the multiple payment distresses and characteristics. They can be extracted using just single set of the data. So you have high resolution of data, you can extract cracking, rotting, and IRI, etc. So this is just kind of selected a journal paper and kind of give you an idea. This is the one we've been published since we are not only national, but worldwide leading in this area about 3D technology, as well as the using machine learning in this area. So you can see that I just selected 4 recent papers published in the machine learning and on the cracking automatic detection and using smartphone, as well as 3D technology, the payment condition assessment, as well as automatically detect and classify the raveling using 3D technology and machine learning, as well as using machine learning for the joint plane concrete, the detection, as well as a pothole payment cracking and raveling and concrete joint rotting, etc. So I just want to note that to mention about is 3D technology not only for the network label condition assessment. We kind of get into the automatically the payment construction quality control, like the payment texture using the RBD. That's the one. So the second one there, sensor technology is using LiDAR. So as you can see, the LiDAR, on the left-hand side in our Georgia Tech sensing vehicle, you have the camera and you have the LiDAR. There's 2 systems showing there. One is Rico, the other one is a SICK LiDAR. And then you can see on the right-hand side that is collected on the Georgia's roadway. So on the top is 2D image, on the bottom is a LiDAR cloud. So you drive through, you can getting the XYZ as well as the retro intensity data. So all of those data can be extracted. Then we perform the data analysis and data processing and data analysis. In our analysis, we're using the entire interstate highway and total 2,500 miles. As you can see on the left-hand side, that is each interstate highway. On the right-hand side, those are the entire interstate highway that we are collecting the data for 2015 and 2018 to show it to you today. This one here is showing the one that total 21,000 observed sign has been inventory, and with the accuracy within 5-meter resolution, and been inventory the first time at the in the Georgia, and then those have been put into interstate highway asset management. And also on the right-hand side, you can see the payment. So there are 3 different types of payment: the asphalt payment, as well as CRCP, and JPCP was joint planted concrete payment. So with different colors showing there, that's the distribution in Georgia, and that's what we perform the data collection. So there's 2 objectives for us. One is a traffic sign. So first one here, our goal is eventually try to develop a new national standard. So the current, there's 3 methods in this slide here. The one to the left, the current practice, and most of the state DOT, including Georgia DOT, is using visual inspection every year. So you can see that they need to drive at night and perform one assessment. So it's a subjective and time consuming and nighttime only. In the middle one, that's the second approach, which is the current approach there using retro reflectometer, and which is a lot more objective, but you can see the person need to shooting the sign 4 point. It's time consuming, dangerous, and then it's only a 4 point. So what we propose, the new approach there is using the mobile LiDAR. So it's driving 100 km/h, shooting all the data point, and it provided objective assessment. You can see that driving through 100 km/h, then you can get the data more than 100 point, not 4 point like second method. So, and then you can perform the assessment anytime. You don't have to do that at night. So that's the beauty on that. So what I did is the study here, as you can see that we kind of established a new approach here. It's called LiDAR-based categorical sign ritual reflectivity condition assessment, basically nighttime visibility condition assessment. So the first step here, we establish correlation between the ritual reflectivity and the mobile LiDAR's ritual intensity. As earlier I mentioned about LiDAR cloud, the collect XYZ, the coordinate as well as ritual intensity. So we kind of using that data there because that is energy reflect back. So we correlate with the second method in the previous slide and using ritual reflectometer come out with data that correlate them. So keep in mind, to correlate, we are not just number by number, we base on the category. So there's a 3 different category: poor sign, uncertain, and good sign, because we can easily separate the poor and good sign using the LiDAR approach. And then, so that's the philosophy or rationale that we have. So develop a criteria, sign ritual reflectivity category using the LiDAR's, the ritual intensity, which is from the LiDAR cloud. The third one there is we validate the outcome by verified by Georgia DOT engineer. And the end, I think fourth one there, we kind of demonstrate that on one of roadway I-285. So on I-285, using the LiDAR, you automatically extract that there's a total of 338 signs were extracted. 67 of them is poor condition, 47 is uncertain, and 224 is good condition. So through this kind of very small set of the data, which is I-285, you can get an idea that almost 67% of the AFIR, the sign, the good condition, you probably through that processing data, then it can be extracted. And so the people probably need to focus on those 33% of the sign to take a look, because those are poor or uncertain condition. So on the left-hand side, those 2018 I-285, the color green is good condition, red is in a poor condition, as well as the one that showing uncertain there. So just keep in mind, right now is kind of survey once a year using LiDAR data. But in the future, there's a fair amount of autonomous vehicle, connected vehicle, they have a LiDAR. So instead of survey once a year, there's potential with our proposed approach that can assess more frequently to do the safety assessment more frequently. So that's the potential. This is the one showing that using the ritual intensity data, we pull just one of the cases showed it to you from 2015 to 2018 on the lab button there. So you can see that those are the different signs from the 2015, the same sign, and then extracted. You can see that originally ritual intensity, the value is much higher and then gradually change. And you can see there's a one thing here, not only the value deteriorates, but also the variation changed. So there's button in the note there, poor sign condition is also reflected by the high standard deviation of ritual intensity value. So all this result here would help the Georgia DOT engineer to understand the long-term deterioration of the sign ritual intensity and predict the optimal timing for maintenance activity. Second one here is related to payment condition, payment distress. So this is the one that the ask for payment, the procedure there is to collect the data, processing automatically, processing QA/QC. And so this one here, ask for payment, that's focused is by the research project, the 1511. This project was also been selected by AASHTO as the high value research through the national competition. And so, but this project earlier putting together is asked for focus on the automatically the payment condition, ask for payment condition evaluation using 3D technology, but that is focused on asphalt. But later on in this project, we kind of expanded to the payment, the concrete payment. So this is kind of showing the procedure there. still collect the data in the end. And not only the concrete payment, we also extended to IRI, which is using the same data set. Can I extract not only distresses, but also IRI? So you don't have the second type of device to collect IRI again. So you also concrete slab classification, and then also joint faulting, etc. You can get that result. So this slide here is showing that the data collected in 2018 using the sensor technology on the left-hand side is asked for payment. There's total 10 different distresses and being combined together, and it comes out as overall rating. And you can see that the red color indicated poor payment condition, and green color indicates a better condition. On the right-hand side, that's the concrete payment, so you can see that. And this one here also see the change too. So 2015 and 2018, if you take a look on the left-hand side, this is kind of showing the asphalt payment. So on the left-hand side, you can see some of the circle area there. If you take a look on the right upper portion, which is I-85, you can see on the left-hand side in the 2015, still in a good condition, but when you get into 2018, the condition is not very good because it's kind of getting pretty red. And you can see the I-75, the going to the Tennessee border, it's almost there's some resurfacing happening, and because it's been changed in a better condition in 2018. So besides the condition there, that we also collect the IRI, because the same sensor data, I just collect one data, which is high resolution data, and just automatically extract different type of the information. This one here is IRI information. So you can extract that. So based on 2018 data, you can take a look in the entire interstate highway in Georgia. You can see most of them is a very good condition and good condition. So it's only in 1% based on the FHWA standard, the IRI, which is smoothness, is in a poor condition, only 1% there. So I think I would get into a conclusion. So what's the impact and benefit through our research project? So one of them there is the collected sign inventory payment condition data collected in 2015 as well as 2018 has been already used by Georgia DOT for its interstate assets management. So that has already been used. And developed a categorical traffic sign retro reflectivity condition assessment method using the LiDAR technology can complement the commonly used nighttime sign condition assessment method currently used to save the sign inspection effort by focusing on the signs that need most attention, like a poor and uncertain category, as earlier I mentioned about. And it is recommended to have a large-scale pilot study to further implement the developer method. I think we're using an I-285 testing on that. It seems like quite promising, and so it's kind of recommend to have a large-scale pilot study to further implement the developer method. The second one here is it showed it to you the deterioration trend that can be further studied, and it can be used to predict the optimal timing for sign replacement. So that way you can do the planning. So this is in terms of using the 3D LiDAR technology. In terms of 3D laser technology, with the automation method, have demonstrated to be cost effective. This impact GDOT making the decision to adapt the 3D laser technology for its automatically payment condition evaluation. In addition, in 3D laser technology with the automatically payment condition evaluation has also become a mainstream technology in the US for state DOT's payment condition evaluation. So the all this automation method here, the one we study in the research, is for collecting the sign and payment condition can also enhance safety by eliminating the workers' exposure to the roadway hazards. And this is the one just kind of showed it to you in terms of 3D technology. We have the also kind of continue putting and then impact the national standard because we are kind of nationally an worldwide leader in this area, 3D laser technology for automatically payment condition evaluation. So the first one there we already finished, and we create a new standard, open format standard. It's called .psi payment service image. It's similar like JPEG. And last year is already evaluated but passed the technical review. This year it's going to be published by AASHTO standard. So every state DOT is going to follow the standard we put together. So that's the first one here. And the second one there, we are in the process sponsored by NCHRP to develop another 5 to 6 standard, national standard about the 3D technology, the quality control. So with that, I will stop here to answer any question.
All right, thank you very much. I know that we're right against the 2 o'clock hour right now, and I actually have a meeting I have to run off to with the Federal Highway Administration. So I'm going to leave it up to Robert as to whether or not we can take any questions and run over. But before I go, I'd like to thank all of our speakers for attending today and for doing such a great job on these presentations. Robert?
We have time to take those, and I can stay in for as long as the speakers want to stay around and answer any questions. We can also do breakout rooms for the speakers themselves if they would like, or feel free to contact any of the speakers via their contact emails if you have further questions. I'm sure all of them would be more than willing to help or to spend more time discussing their projects with you.
And Robert, you have all of the attendees' emails too, so perhaps we can follow up with additional information for anyone who's interested.
Yes, that is correct.
All right, I'm going to let you take over, and I'm going to go ahead and head over to my Federal Highways meeting. Thank you, everybody.
Thank you, Randy.
Thank you.
Thank you. So does anyone have any questions they'd like to ask any of our presenters?
It looks like Jewel has a question for Dr. Tsai.
Oh, I see.
In the chat.
In the chat where I can see the chat.
Well, here I can read Dr. Tsai.
Sure.
Go ahead, Robert.
Yeah. Is the extraction of the reflectivity from the LiDAR an automated or manual process?
Yeah, I think at this point of the time that is semi-automatically. So we extract that and then we aggregate specifically. I think, for example, when we extract the sign for a specific sign, those are automatically extract. And once we extract the sign based on 2D location, we extract the 3D LiDAR point, cloud point. And then through that one there, that's automatically processing. But we go through some of the QA, QC, those are the semi-automatically to make sure all the processing there has been collected, especially in the automatically sign detection portion there. It may be 80% or 90% of sign detected, but there's 20% not being detected. That process there is the kind of manually checking. So it's kind of combined with the semi-automatically process now.
The next question is for Dr. Kwan. Did you find any correlation analysis between UCS and Modulus values?
That's a good question. Actually, that's one of the objectives of the new project, 2014. And we try to kind of establish a correlation between the UCS and then the Modulus values, because there are several different the correlation equations are available. Depends on how you characterize those, the FTR base. So that's the part of the new project. Robert, you're muted.
I am unmuted. Yes, sir. Dr. Durham, how does your analysis compare to the full-scale truck crash barrier testing?
Yeah, that's a great question, Jewel. And so in our research with the finite element model that we had built for the barrier wall and the single unit truck, that is simulating that full-scale truck crash impact on the barrier wall. So we utilized the angle of the truck, the weight of the truck, all impact on the barrier wall. And really the next step, if we were to move forward, would be to go to one of the testing centers, to be able to do that full scale testing. At this stage here, we still feel like there's still a lot of work left to be done in evaluating large-scale batching of rubberized fiber reinforced concrete. I think one of the things we observed in our large-scale barrier wall testing in the lab was that the ready mix production of that rubberized fiber concrete saw some quality issues from an air content standpoint, some other things. So I think there's probably still a little bit of work to be done there, but then ultimately to be able to go to the actual experimental testing at one of those testing centers. Great question.
Thank you, Dr. Durham.
And yes, Jewel, absolutely. I can certainly share the final report. Actually, I can send you a PDF copy of that, and then if you want to pass it along to others, please do.
All right, well, in seeing no more questions, I want to thank our presenters. I want to thank our GDOT guests and our other guests from around the state. We look forward to doing this again. We're hoping to make this a regular monthly kind of event to do webinars to support GDOT, GTI projects that are going on throughout the state, just showing all the successful transportation research we're doing here in the state of Georgia. Again, thank you, each of y'all, for your time and today.
Okay, thank you very much.
Thank you.
Bye.